Hi students. So in this session we are going to see the problems on heat transfer. So in heat transfer, we know conduction. Okay, in conduction, uh, heat current, heat current, thermal conductivity. Okay, then in radiation we know Stephen's law, Stephen's law, then Wien's displacement law, Wien's displacement law. Then other than this, we have uh, this absorption, transmission, then reflection. Okay, then uh, absorption for a particular wavelength, the absorption, emission, transmission, reflection. Okay, all these things we have seen. So Stephen's laws, Wien's displacement law, then Newton's law of cooling. So from all these topics, numericals or questions can come. Okay, so one by one, so it's necessary formulae concept we will discuss in the question when we do. So we will start. So first question is one phase of aluminium cube of edge 2 meter is maintained at 100 degrees Celsius and other end is maintained at 0 degrees Celsius. All other surfaces are covered by adiabatic walls. Find the amount of heat flowing through the cube in 5 seconds. Okay, suppose if this is the cube, suppose if this is the cube. Okay, fine. So here one side is maintained at 100 degrees Celsius and the other side is maintained at 0 degrees Celsius, and they are saying like it is covered with the adiabatic walls. Adiabatic walls means there won't be any heat loss, and its edge is 2 meter, means its length, breadth, width, everything is 2 meters. Okay, that is also given. Now we need to know what is the amount of heat flowing through the cube in 5 seconds. So Q by T, we need to find it out. Okay, so Q by T is what is heat current. Okay, heat current. So Q by T or heat current is equal to what? So its formula was Ka by L Th minus Tc. Okay, Ka is thermal conductivity, A is area, and L is the length of the conductor. So Q by T is this. Now what we need to find, actually we need to find the amount of heat flowing, find the amount of heat flowing. So amount of heat flowing is Q. Amount of heat flowing is Q. Okay, so Q is equal to K is given 209 and area is not given but edge is given, so we can understand the cross sectional area is 2 square, and Th temperature at higher temperature side is having 100 degrees Celsius and this is minus 0, divide by L length, that is again 2 meter, into time T, that is given as 5 seconds. Okay, so if we simplify this, 209 into this 2 square will be cancelled off, this is 2 and this is 100 into 5. So 5 into 2 is again 10. So we can note that 10 raised to 3. So 209 kilojoule. This is the amount of heat flowing through the cube in 5 seconds. Okay, so this is a question on thermal conductivity. Okay, shall we move to the next problem? Okay, this is another problem. So this is okay. Three identical rods of length 1 meter each, having cross sectional area 1 centimeter square. So length is same for everyone, 1 meter length, and the area of cross section is 1 centimeter square. This is made of aluminum, copper, and steel, and their temperatures, they are kept at the temperatures 12 degrees Celsius, 4 degrees Celsius, 50 degrees Celsius at their separate ends. Find the temperature of their common junction. Okay, so this is the junction. Here we need to find the temperature. Okay, and thermal conductivity is given. So already when while discussing the theory, already we have seen lot of similarities between this heat current and the general current in current electricity. Okay, the charge of flow of charges. Okay, so that is it. So we have studied we study Kirchhoff's current law in current electricity. Same thing we can apply here. So what I am going to do is, this is one side, this is another side, this is the third side. I assume that, okay, just for solving this problem, I assume that this junction is having the highest temperature. Okay, the maximum temperature or highest level of temperature is at this junction. So I assume that heat current will be flowing in the outward direction. All heat currents will be flowing in the outward direction. So practically what is going to happen, from one side it is going to enter, to the other side it is going to separate and go. But for solving this question, I assume that everything is leaving. But while doing the answer, while getting the answer, we will be getting negative sign for some answer. So we can understand that that is in the opposite direction, entering side. So this side it is 12 degrees Celsius. This side it is 50 degrees Celsius. This side it is 4 degrees Celsius. So the sum of heat currents, okay, will be equal to 0. Okay, the sum of entering and leaving current will be 0. Whatever heat current entering to this junction will leave. Okay, so the algebraic sum of, so this 50 degrees Celsius, this is steel, this is copper, and this is aluminium. Okay, so the sum of heat current will be 0. Entering will be leaving through some side. So heat current in the aluminium rod plus heat current in the copper rod plus heat current in the steel rod is going to be 0. So what we shall do, K aluminium A by L plus K copper, I'm sorry, here, okay, here, yes, TH minus 12 plus K copper A divided by L into TH minus 4 plus, okay, K steel, okay, K steel A by L TH minus 50 is equal to 0. So whatever is entering will be leaving. So sum of all the currents will be equal to 0. Okay, clear or what? Okay, so now we can simplify this. We can simplify this. So here, what we need to understand, this L, A, everything, they are all same. Okay, area will be same. So area will go to that side. L will go to that side. Finally, what will be available here? Here, uh, whatever this 12 degrees Celsius, Th minus 12, and this thermal conductivity also will be there. So this is 200 into Th minus 12 plus here what for copper it is 50 into Th minus 4 plus for steel, what is for steel? For okay, this one is steel actually. Okay, this 50 is for steel. Okay, here you can make this correction. This is actually steel. Okay, this is steel. Okay, so here 50, here I shall correct it as 400. Okay, this is 400, and for steel we will give 50 into Th minus 50. This is equal to 0. So now when we simplify this, mm, we will be getting 200T minus 2400 plus here 400 into Th, 400 into T, all of these are Th, then 400 into 4 is minus 1600 plus, then what, 50 into Th, 50 into Th minus 50 into 50, that is 2500, minus 2500 is equal to 0. So clear? Yeah, are you able to understand? So here this is going to be 650 Th is equal to, this is 4000 and 6500, 6500. So Th is equal to 10 degree Celsius. So this temperature of this common junction we are getting as 10 degrees Celsius. So one thing is clear, that from 50 degrees Celsius, from here actually, see, I shall mark the answer in red color. So this is 10 degrees Celsius. So from 12 degrees Celsius and 50 degrees Celsius, obviously the heat current will be coming into this, because they are at a higher temperature side. And to 4 degrees Celsius, the heat current will be going. That is going to be the correct direction, if we say. Okay, clear? So this is just like how we can handle the current, the same way we can handle. So here the heat current we will have to consider. Okay, Ka by L, Th minus Tc formula, and all the currents I have considered as leaving current. I took the algebraic sum is equal to 0, and finally I am getting the uh, this node temperature. Okay, is it clear for you? Okay, shall we move to the next problem? So this is the final answer. Okay. Okay. So here, this is the next problem. Okay. Okay. So here, find the heat current. Find the heat current. So T1, this is the higher temperature, Th, and this is at lower temperature. This T1 upper, T2, this lower arrow is the indication for that. Okay. Okay. So here, this resistance, if we consider this as resistances, then what about the combination? This is actually series combination, right? This is actually series combination. So what is the resistance here? If we consider thermal resistance, Ka by L, Ka by L is actually what? So in this question, they are asking what is the heat current. So heat current we know H is equal to Ka by L Th minus Tc. So this is just like suppose if current is asked, this voltage divide by resistance. So instead of that, if we are writing conductance, okay, instead of resistance, if we write conductance, I is equal to kv in this form. I is equal to v by r is resistance. So if we take resistance from this formula, h is equal to what? Th minus tc divided by L by Ka. This is just V by R form. Okay, just like current I is equal to voltage difference divided by resistance. Same way, heat current is equal to temperature difference divided by resistance. We can take into this form. Now these slabs are connected in series. Series connection already we have discussed. This is going to be what? Th is T1 here minus T2 divide by the resistance of each one. So L1 divide by K1A plus L2 divide by K2A plus L3 divide by K3A. This is going to be the heat current. So option C is correct. Okay, hope you understood. So we have made small modification in the formula. Instead of putting it in the conductance term, thermal conductance, we have put it in the thermal resistance terms. Then we are getting this answer. Okay, hope you are comfortable. Shall we move to the next problem? Okay, so here this is the next problem. The total mm, the total radiation incident on a body is 400 joule. If 20 percentage of incident radiation is reflected back, 120 joule is absorbed by the body. Then find out the transmittive power in percentage. Transmittive power means nothing but the transmission, how much percentage of radiation is transmitted. Okay, right. So q is equal to, already we have studied this, q is equal to what? The quantity of radiation absorbed, the quantity of radiation reflected, plus the quantity of radiation transmitted. So 400 is equal to here, 20 percentage 20 percentage of the radiation is reflected back. 20 percentage is reflected back. So what is qr? 20 by 100 into 400. So this 400 is the total radiation. From the 20 percentage of this 400 is this much, that is 80. So qa, okay, qr is this. qa is 120 is absorbed by the body, that is directly given. So 120. Qr is going to be 80 plus this is qt. So qt is what? Qt is going to be 200 joule. So what they are asking is transmitted power in percentage. So qt is actually in percentage 200 divided by the total, that is 400 into 100. Okay, so this is going to be how much? 50 percentage. So 50 percentage of the radiation is transmitted. Clear? We found the percentage of transmitted radiation. That's it, nothing else. Clear? We'll move to the next problem. Next problem is if lambda m for moon is 14.5 micron, then its temperature is. What is its meaning? The maximum intensity of radiation from moon we observed at which wavelength? At lambda m. So we know Wien's displacement law. What is Wien's displacement law? Lambda m, that is not maximum wavelength, but the wavelength corresponding to maximum intensity into T is equal to what? Wien's constant. So in order to find the temperature, B by lambda m. What is B? 2.89. Wien's constant is 2.89 into 10 raised to minus 3. Okay, you divide by lambda m is 14.5 into micron 10 raised to minus 6 meter. Okay, clear? So now when we solve this, we'll be getting 199.3 Kelvin. So from sun or moon or from whichever source, by analyzing that spectrum of radiation, taking its maximum intensity and its corresponding wavelength, that if we deal with this Wien's constant, we will be getting the temperature. So we can measure the temperature of distant bodies using Wien's displacement law. That is the power of this. Clear? Next problem. Yes. The operating temperature of a tungsten filament in an incandescent lamp is 200 Kelvin. Its emissivity is 0.3. Find the surface area of the filament of a 25-watt lamp. Stephen's constant is given. Sigma is equal to 5.67 into 10 raised to minus 8. Okay. So here they have given like a 25-watt lamp. 25-watt lamp is what? If we consider the rate of emission is what? The total radiation emitted divided by time t. This is same as wattage. Okay, so this is given. Now what we need to find? We need to find the surface area. So we know Q is equal to what? Emissivity into sigma, that is the Stephen's constant, into its the area of that the surface area of that thing. Okay, the radiating um, thing. Okay, radiating, where this is filament. Okay, radiating body. Okay, into T raised to 4 minus uh, this is the body and this is the surrounding Ts raised to 4. Okay, into what? Into time. This is the total radiation, that is net radiation. Okay, net radiation. But here here they haven't given the net radiation, but what they are giving is the surface area of the filament of 25-watt lamp. So here we are not going to consider the surrounding means whatever is incoming, whatever is outgoing. With this we will be able to find the net radiation that is coming in or moving in. So simply going out, okay, outward radiation is E sigma A, temperature of the body raised to 4 into T. What we are asked to find out here, we need to find area. So area is Q out divide by T into here 1 by what? E sigma A, temperature of the body raised to 4. Okay, so Q out by T is 25, divide by emissivity is given as 0.3. Stephen's constant is 5.67 into 10 raised to minus 8. Okay, here area already we have written here. Okay, fine. Now what? Temperature of the body. Temperature of the body is given as 2000 Kelvin. So 2000 raised to 4. So simplify this, will be getting 0.918 into 10 raised to minus 4 meter square. Okay, so this is the area of the body. Clear or what? Okay, so the formula which I have written first is the net radiation. That is the net radiation that is going in and coming out, considering all incoming and outgoing together. But here we have given about the power of the lamp. That is, we need to consider only outgoing radiation. So I wrote the second formula. So from that, area is equal to Q out by T into 1 by the remaining numerators on the right hand side. Q out by T is the rate of emission or wattage or power. Okay, so that is given as 25 watt. Then remaining things we substituted, got the answer. Clear or what? Next problem. Calculate the temperature at which a perfect black body radiates at the rate 5.67 watt per centimeter square. Stephen's constant is also given. Okay, so here, okay, so Q by T is given. Okay, what is this? Radiates at the rate Q by T. Here we can say 5.667 watt per centimeter square. So from the unit, we must understand this is given as a radiation per unit area per unit time, because 5.67 watt centimeter square they have given. So Q by TA, or while discussing the theory, we have written E. This is equal to 5.67 watt centimeter raised to minus 2. This is what is given. Now if we need to convert this into meter square, okay, because the Stephen's constant, everything is given in Kelvin, meter raised to minus 2. Let us convert this into 5.67, okay, into, so per centimeter square, so 10 raised to minus 4 should come in the denominator, so 10 raised to 4 watt meter raised to minus 2 we are getting. Now E is equal to what? Sigma T raised to 4. So what we need to find? We need to find the temperature of that body. So T is equal to E by sigma all raised to. So in order to remove this raised to 4, power of 4, we shall put here 1 by 4. So 5.67 into 10 raised to 4 divide by, here again 5.67, Stephen's constant, 10 raised to minus 8 all raised to 1 by 4. Okay, so this is what? If we this will cancel, this will become 10 raised to 12 all raised to 1 by 4. So 12 into 1 by 4 is what? 3. 10 raised to 3. So this is going to be 1000 Kelvin. Clear or what? Okay, hope you understood. Okay, E is nothing but Q by TA, that is radiation per unit time per unit area. That is very visible from the unit. So we must be very careful while handling this. Look at the unit and understand the sentence so that it is easy for us to deal. Okay, clear. Shall we move to the next problem? Yes. So here the temperature of furnace is 2000 degrees Celsius. In its spectrum, the maximum intensity is obtained at 4000 Armstrong, that is lambda m. If the maximum intensity is at 2000 Armstrong, then calculate the temperature of the furnace. Okay, clear. So Wien's displacement law, lambda m into T is equal to B. Okay, so here two situations are given. So lambda m1 T1 is equal to lambda m2 T2. Okay, so here 4000 Armstrong into, okay, Armstrong, left hand side and right hand side, it will get cancelled off. If we deal this in SI unit, both side it will get cancelled off. Temperature we must take in Kelvin, because the temperature conversion can be done by adding 273. That will not be cancelled off. So if we directly do, since the answer they have asked in degree Celsius, if you put in degree Celsius, you will be getting a different answer. And if you do in Kelvin scale and convert into Celsius in the end, that will be different answer. So while doing this problem, you need to be very careful about the units. So I shall show you. So T1 is how much? 2000. So I am going to write here 2000 plus 273. Okay. This is equal to lambda m2 is what, 2000 Armstrong into temperature T. So this we are going to get in Kelvin because we have converted this in Kelvin. So if we find this Tk, this is going to be what? This cancel, this will become 2. 273 into 2. Sorry, 2273 into 2, we will be getting 4546. 2546. This is T2. Now T2 in degrees Celsius, if we do 4546 minus 273, if we do, we will be getting 4273 degrees Celsius. This is the answer for this question. If we do 4000 into 2000 is equal to 2000 into T, the answer which we are going to get will be different. See, to 4000 into 2000, this is equal to, okay, this is equal to this temperature is this is 2000 into T, which we need to find. So immediately the answer will be T is equal to 4000. Definitely this will be there in the options. If you think that we can do like this will be there in the options, but this is wrong answer because the unit conversion will not be correct here. Okay, Armstrong and Armstrong will be cancelled off. That is why we don't need to worry about this. But Kelvin, Celsius, it is the unit conversion is by addition, so it will not cancel. Clear or what? So here the unit we need to be very careful. Clear? Shall I move to the next problem? This problem is very easy, but a trick is here. A trap is hidden here. Okay, another question. Two bodies A and B have thermal emissivities of 0.01 and 0.81 respectively. Okay, the surface areas of outer surface areas of two bodies are same. Area is same. Two bodies emit total radiant power at the same rate. Okay, fine. Radiant power, that is also same. That is Q by T, Q by TA, all are same. The wavelength lambda b corresponding to maximum spectral radiancy of B is shifted from the wavelength corresponding to maximum spectral radiancy in the radiation of A by zero point 0.1 micrometer. That is, lambda m of B and lambda m of A, they are at a distance of 0.1 micrometer. That is what they are saying. If the temperature of A is 5802, then calculate the temperature of B and wavelength A. Okay, that is the question. So let us write the emissivities and datas. So the emissivity of body A is 0.01. Emissivity of body B is 0.81. These are given. Now, area of A is equal to area of B. That is also no worries. QA by T. Okay, this is equal to QB by T. They are very clearly written like the total radiant power. They emit total radiant power at the same rate. That is also same. So power is also same. We know the radiation is what? Radiation is equal to E sigma A T raised to 4 into T. This is the total radiation that is emitting from the body. Clear? Right. So from this, what we can understand, sigma is constant, A is constant, A is same for both. Sigma is constant. Okay, Stefan's constant, that is constant. Area of both the bodies are same. Area of both the bodies are same. Now, Q by T is also same. This Q by T is also same. So in this, we can understand that EA Ta raised to 4 is equal to Eb TB raised to 4. So only EA and EB is different. Temperature of A and temperature of B is different, but their products are same. Okay, so we are equating this. Remaining all the things will be cancelled off. Okay, so from this TB, temperature of B, we need to find TB raised to 4 is equal to EA is 0.01 divided by 0.81 into TA is how much? 5802. 5802. So here, what I am going to do is this 0.01 we shall make multiplying and dividing with 100. We will be getting TB raised to 4 is equal to 1 by 81. I'm sorry, here raised to 4 is there. 1 by 81 into 5802. Okay, raised to 4. Now, if we need to remove that power 4, we will remove this power 4. TB is equal to, what about 1 by 81 raised to 1 by 4? This is actually 3 raised to 4 is what is 3 raised to 4 is equal to 81. Okay, 3 into 3, 9, 9 into 3, 27, 27 into 3 is 81. So this is going to be 1 by 3 into 5802. We will be getting temperature of body B is actually 1934 Kelvin. So this is the first answer. Answer for the first question. Temperature of B is this. Okay, please go through the solution. Are you okay? Okay, they have given like the radiant power is same, area is same. Okay, so QA by T is also same. Okay, so the only thing which is different is emissivity and the temperature of the body, and their products is also same. So we found temperature B. Now we need to find the wavelength lambda A. Okay, so lambda A into TA is equal to lambda B into TB. And one thing we know, which temperature is more, uh, TA TA is equal to how much? 5802, and TB is equal to 1934. So obviously lambda A and lambda B will be greater, because lambda into T is equal to what? Constant. Okay, lambda T is equal to constant. So obviously lambda B will be of high value. So lambda B minus lambda A is equal to 1 micrometer. Can I write like that? See, they have given the wavelength lambda B corresponding to maximum spectral density of B is shifted from the wavelength corresponding to maximum spectral density in the radiation of A by zero point 0.1 micrometer. So I have written like this. Okay, let it be there. Now, uh, from this, we can write lambda B is equal to lambda A TA divided by TB. See what they are asking? We need to find the wavelength lambda A. We need to find the wavelength lambda A. Lambda B is given. Lambda B is also not given actually. Okay, both are not given. So let us find this. Now lambda B is equal to lambda A into what is TA? 5802 divided by 1934. So if we cancel them, this is 3. We will be getting lambda B is equal to 3 lambda A. Okay. Now lambda B is 3 lambda A. Now from this equation, okay, 2 in 1, we will be getting 3 lambda A minus lambda A is equal to 1 micrometer. So 2 lambda A is equal to 1 micrometer, and lambda A is equal to how much? 0.5 micrometer. Correct or what? Is it true? No, this is 2.1 micrometer. Oh, okay. This question, is it 0.1 micrometer? The difference is actually zero point 0.1 micrometer. Okay, so here while typing there is a mistake here. This is actually not zero point 0.1, this is actually 1.0 micrometer. This is a typing mistake. Okay, fine. So please correct it. Okay. So okay. So lambda b minus lambda a is 1 micrometer. So lambda b is how much? Lambda a. So 3 lambda a. So 3 lambda a minus lambda a is 1 micrometer. So this is going to be lambda a is equal to zero point 0.5 micrometer. So lambda b is how much? Lambda b is 3 into lambda a. So 1.5 micrometer. This is the answer for this question. Lambda b is 1.5 micrometer. Is it clear? So this is a good question, tricky one. Okay, please do this. Okay, so first one, we understood what is temperature. So from temperature, we put the relation lambda a Ta is equal to lambda b Tb. So lambda b minus Ta is 1 micrometer, which is given in the question. Okay, so based on that, from the relation we got the relation between lambda b and lambda a, that we substituted in equation 1 and got the answer. Okay, clear? Shall we move to the next problem? Okay. So next problem is about Newton's law of cooling. Assuming Newton's law of cooling is valid. Why this assumption is made? Because if there is big difference between the body and surrounding temperature, then Newton's law of cooling is not valid. So we need not think in that level. That is the reason they have given. Just consider Newton's law of cooling is valid. Temperature of the body changes from 60 degrees Celsius to 40 degrees Celsius in 7 minutes. Temperature of the surroundings is 10 degrees Celsius. Find its temperature after next 7 minutes. So there can be a natural temptation like from 60 degree to 40 degrees Celsius. The difference is how much? 20 degrees Celsius. So 20 degrees Celsius is the difference in 7 minutes. So in next 7 minutes, again, if further 20 degrees Celsius change is there, the answer can be 20 degrees Celsius. But we cannot do like that. Like if we do like that, things may go wrong. So we will stick to the formula of Newton's law of cooling. So the formula for doing numericals, I had given a separate formula. That is what? T1 minus T2 divide by T. What is this? This is final temperature minus initial temperature of the body divide by T. Means that this is rate of cooling. This is equal to a constant into the average temperature of the body. Okay, average temperature between initial and final. Okay, minus T naught. What is T naught? T naught is the surrounding temperature. T naught is the surrounding temperature. So first is 7 minutes. Let us see. 60 minus 40 by 7. So certain things which I need to tell you in this: maintain time, maintain T in minutes while solving this question using this formula. First point is maintain time T in minutes itself. This is surrounding temperature. This is surrounding temperature. T1 and T2 is final temperature of body, and T2 is initial temperature of body. Okay, so remember this thing, this is constant. Okay, so fine. So now we do not know the constant, we need to find the constant and we will put in the next step, that is next 7 minutes. So 60 minus 40 by 7 is equal to K into 60 plus 40 divided by 2 minus surrounding temperature is given as 10. So maintain it like that. Okay. Okay. So here we can maintain the temperature also in degrees Celsius. This is one point. Another point is temperature can be maintained degree Celsius. So this is a technique to solve problems when Newton's law of cooling is asked. Okay. Use this formula, that will be easy. So 20 by 7 is equal to K into, this is 50 minus, this is going to be 40, and we will be getting K is equal to 1 by 14. So we are getting here the constant K is equal to 1 by 14. In now next 7 minutes, what will happen? So here now the final temperature was 40. So in the next step, T2 we do not know. T1 is equal to 40 because in the first 7 minutes, temperature of the body became 40 minutes, 40 degrees Celsius. So T1 is equal to 40 here. Okay, so 40 minus T2 divide by 7 minutes. In the next 7 minutes, what will be the temperature of the body? This is what they are asking. That constant we found 1 by 14 into 40 plus T2 divide by 2 minus surrounding temperature 10. Okay, clear? Now 40 minus T2, this is equal to, this is again here, this is 2. So 40 plus T2. So here, if we multiply this 2 inside, okay, multiply this 2 inside, we will be getting, this will become 4 here, 10 by 2, 5. So minus 20 we will be getting, and this divide by 4. Okay, so simplify this, we will be getting 160 minus 4T2 is equal to 20 minus 20 plus T2. So 5T2 is equal to 140. T2 is equal to 28 degree Celsius. Okay, so this is a problem using Newton's law of cooling. Okay, so please go through. The step is like T1 minus T2 by T. This is the rate of cooling. Okay, is equal to constant into T1 plus T2 is the average temperature of the body. Okay, considering initial and final temperature. T1 is initial temperature, T2 is final temperature, minus T naught. T naught is the surrounding temperature. So in the first 7 minutes, they have given final initial temperature, temperature of the surrounding, everything except constant. So that constant we found. The question is like find the temperature of the body next in the next 7 minutes. So here in the first 7 minutes, the temperature of the body became 40 degrees Celsius. So here in the next step, 40 degrees Celsius is the initial temperature. So 40 minus T2 divided by 7 minutes is equal to that constant into 40 plus T2, that is initial plus final, divided by 2 minus the surrounding temperature. So solve this, we will be getting the answer. Clear, children? Okay, so this is the basic fundamental discussion on heat transfer. Also we have done problems from each area. Practice this and practice more number of problems. Okay students, okay, study well. Goodbye, good luck, thank you.